Hello everyone, thank you for being here. Now this is a story all about how our view of the solar system got turned upside down. And if you listen to my talk for just under an hour, I'll tell you how we think we know how many planets there are. So let's get the obvious thing out of the way first, right? If you're an old person like me, you grew up in a solar system that was composed of 9 planets. And of course there were ways to memorize the names of the planets. And English is not my first language, but when I researched what these were, I encountered this data. So my very educated mother just served us 9 pizzas is a popular one, but you get several variations of this. The mother could be eager, could be energetic, and the food could be different. But this was a way of memorizing it. Now in German there was just one and it was very popular. Mein Vater erklärt mir jeden Sonntag unsere 9 Planeten. Now obviously both of these no longer work in a solar system of 8 planets, but also if we want to go to literary criticism, I don't like the fact that it's always the father in the German version. And I don't like that it's just about random food in the English version. So if we update this, we get an English version that was actually recommended by astronomers, so it's kind of official. My very educated mother just served us nachos. I mean, I like the fact that it's now definitely the educated mother, but still it's about random food, and the food is not even healthy. So when I was writing my own astronomy books, I came up with this one. Mit Vergnügen erklärt Mama jeden Sonntag unseren Nachthimmel. So now we have mom involved, and it's about astronomy. So thank you for coming to my talk about the solar system. But let's take a step back and wonder, what even is a planet? How do we recognize them, and how were they recognized through the ages? Because this will help us in understanding the number and the identity of the planets that were known historically. Here I have a picture of the night sky, taken not quite at random. This is about the time of the next Congress. So you can take notes and in 1 year come to me and tell me if this was correct, but it was Stellarium, so I trust the software. We see 2 of today's planets and 1 of the classical planets up there in the picture. So to the upper left you have Mars hanging out in the constellation of Cancer. You have the moon between Castor and Pollux in the Gemini constellation. And then towards the right you have Jupiter between the horns of Taurus. And now I will advance by, I think, 2 months. So here comes another view of the sky. And now, for the same field of stars, the planets have moved, right? Mars has moved from Cancer into Gemini. It's now where the moon was before. Jupiter is closer to one of the horns of Taurus, and the moon is nowhere to be seen. And this is how we can understand the classical meaning of the word planet, which comes from the Greek wanderer. So it's anything that moves across the sky in a way different from the stars. Obviously everything moves, right? You look at the sky and the stars move and the sun comes up and down, but if something moves and it moves differently to the stars or relative to the stars, then that is what you may call a planet. And this is how in antiquity and through the Middle Ages, the classical planets were defined. It was anything in the sky that didn't move like the stars. So it's logical to assume that the moon is one of them. We just saw how it moves across the sky. Then we have Mercury and Venus, which are close to the sun. The sun itself was considered a planet because it moves across the sky in a way different from the stars. And Mars, Jupiter, and Saturn were known. Now, this is the way that people understood the sky and kind of thought of our surroundings in the universe in those days. We have to clear up one thing and give some credit to people in antiquity. They did not actually believe that the Earth was flat. This happened a few millennia ago. But mostly, the idea that people up until the Middle Ages thought that the Earth was flat is itself the myth of the flat Earth, which, this is true, was thought up in the 19th century by United States American authors, just people who were just, for a living, making shit up. And they said, you know what? Up until Columbus, people thought the Earth was flat, and he was going to sail around it, and nobody believed him until he did. So this was basically to make Columbus look good, but it was completely made up. And of course, both of these facts are different from the fact that today there are simply crazy people who would tell you that the Earth is flat and who refute any kind of evidence. And if you want to get a clearer overview of this, I just recommend these 3 Wikipedia articles because they clear up the situation quite nicely. Now, the people knew that the Earth was a sphere, but they did believe that the Earth was in the center of everything. And from today's standpoint, it's easy to say, well, that's arrogant. Everyone thought we were in the center of everything, and how could we think that? The universe is so big. But think of the way that we perceive the sky and the stars and anything that moves. We are standing here, and everything seems to move around us. Let's look at it from a different way. If I were to ask any one of you to please describe faces of people, maybe faces of people around you, you would look around and say, okay, well, there's some long hair, there's a beard, there's large eyes, and there's brown eyes. You would probably not in the first moment think of describing your own face, because you are inside your own face, and you rarely ever see it unless you take some measures and you take care to look at your face and try to describe it. And in a similar way, people who were standing on the Earth and looking up didn't think about what the position of Earth was relative to everything else that they saw. They just thought that this was where things were happening, and it was happening all around them. But still, this view of the universe evolved, and they tried to make mathematical descriptions of it. This is a manuscript from medieval times, and I can't read the script either, but what you can see is that mathematically, or by the physics that were involved, it was a very, very complex explanation of how things were supposed to move. And these circles on top of circles, they're called epicycles. And this was a mathematical tool that today actually is pretty much not used for anything in physics. But back then, you needed epicycles to try and explain what you see in the sky. Because if the Earth is at the center of everything, and that the sun and the moon and all the other things are moving around us, then only by employing these very complicated epicycles can you try and explain what you see. But of course, they have no physical equivalent in the real world. These epicycles don't exist. They were just, it was necessary to make them up to try and explain what people were seeing. And then came the first revolution of our understanding of the solar system. And it was about what's in the center. So now comes the shift in perspective when it was realized that in fact it's not the Earth in the center of the solar system, but it's actually the sun. And this is the meaning of the word heliocentric. And with the sun in the center, we then get a different number of planets for a start, because the moon also was no longer considered a planet equal to the others, because the moon moves around the Earth. And from the beginning of the 17th century, it was also clear that also Jupiter had moons. You can see that towards the right, there's 5 little balls, and that's actually Jupiter and its 4 largest moons. And so it was realized that our moon is something different. Other planets also have moons, and that there are 6 planets in the solar system, and our Earth is one of them. Now, this started around the middle of the 16th century. The idea was first published by Copernicus, actually from his deathbed, which is how afraid he was of the church. He said, if I publish this right before I die, then you can't hurt me anymore, which actually says something about the church, right? Because the church would say, oh, no, after death, we still own you. But apparently he didn't think so. Then came Kepler's laws, which were some of the first steps towards understanding mathematically what was going on. Kepler's laws were basically the updated version of the epicycles thing. It was now a clear, a much simpler way of mathematically describing what was going on. And then came Newton's laws, and with understanding gravitation in the way that was described by Newton's laws, things really moved into a modern understanding of the solar system. Basically the same kind of mathematics that still mostly allows us to steer space probes even. If you send a space probe to Jupiter and it's going to orbit one of the moons, that's basically the same mathematics that you had back then. You need to take into account special effects which they didn't have, but mostly the mathematics was already there in that time. But things were changing, mostly because instruments were getting better, telescopes were getting better, more people were having telescopes and looking at the sky. Galileo Galilei was among the very first to look at the sky through a telescope. He pioneered a lot of stuff, but more and more people were doing it. And one of the things that was part of this evolution was that in 1781, William Herschel and his sister Caroline Herschel discovered the planet Uranus. And this updated the solar system to say, okay, look, everything we talked about before, it's still true, but now there's another one at the end. And this was fine, and mathematically and from a worldview point of view, it wasn't much of a problem. You just have the solar system like you had before, and you add Uranus way out on the outside. And it was only possible to see Uranus once the telescopes were good enough. I once saw Uranus through a pair of binoculars, which is pretty cool. But of course, back in the day when you only had the naked eye, it wasn't possible to observe it. So in the age of telescopes, Uranus sort of entered the picture. And now comes the second revolution. Things were happening in the inner solar system. Up until now, we had the sun in the middle and a number of planets, and some of the planets have moons, but that's all there's going on. They also saw comets sometimes, but I'm not going to talk about comets today. They just come and go, basically. But now something is going to happen in the inner solar system, and this is the discovery of what is today known as the asteroids. And let's take a look back. I zoomed in the picture that we just saw. So this is from about 1790. When we were looking at the solar system and saying, okay, we've got all these planets in the middle and Uranus on the outside. But look how between Mars and Jupiter on the outside, so it's zoomed now in this crop of the picture. Jupiter is the outermost thing you see. There is a dotted line, like something's missing, like something should be there but isn't. And there's a very good reason why the astronomers making these charts were leaving this dotted line in this place. And we're going to talk about why they thought that something was missing there that should be noted in a chart. 7 planets were known, but an 8th was somehow necessary, they felt. And the reason why they felt that this was necessary is called the Titius-Bode law. I learned it in astronomy. We called it the Titius-Bode Gesetz. It's actually more of a play on numbers. It's not really a physical law. It's more of a thing that happened to work. This is a modern formulation of it. This is not how it was historically described, but it's kind of easy to understand. So if you look at the distance of some planet from the star, expressed in, and that's in the denominator of the first of the left side, 1 AU, which is 1 astronomical unit. Okay, so imagine something is 1 astronomical unit from the sun. This is the distance of the Earth from the sun, 150 million kilometers. And we have a number of planets in the solar system. So you take 40% of that, and you add another 30% of that, multiplied by 2 to the exponent of n. And for n, you put in these numbers in the series. Minus infinity is the first one. Okay, that's a bit kludged in there. And then it goes from 0 to 6, which looks kind of natural. And if you do that, you get a progression of what distance a planet should be from the sun, should be in the sense of just, if we put in the numbers into this thing, right? Someone, Titius and Bode among them, but not the only ones, made up this number series, and if you put in the right numbers, you almost exactly get the distances of the planets as they really are from the sun. So this looked like magic, or as people back then saw it, a sort of divine rule. God made the solar system to make sense, and we can see it in that thing, because if we put in the right numbers, it's almost exactly where the planets are in the solar system. And the dotted line that we just saw is where I blotted out something for the number 3. That's where they thought something was missing. That's where they thought, well, if the Titius-Bode law works this well for all the planets, but we haven't seen something for n equals 3, well, then it must be there. We just need to look better. And that's what they tried to do. Around the year 1800, shortly before, an eminent group of astronomers met at conferences, and they called themselves in German the Himmelspolizei. Like they were going to observe the sky and look for order and make things right. And they exchanged notes on who should be part of the Himmelspolizei. They divided the sky into sections and say, okay, you guys from France, you're going to look in that direction, and you guys from Britain, you're going to look in that direction, and we're going to look really hard in that direction. And when we find something, we write to all the others. And this was the Himmelspolizei, and they were going to solve the mystery of the missing planet for Titius-Bode law n equals 3. And Giuseppe Pazzi from Italy was not part of that group. He was going to be included. Apparently, he didn't get the memo. I mean, the mail was not as reliable as Chaos Post back in those days, I guess. So in 1801, actually on the night of the 1st of January, the very first day of 1801, he discovered the missing thing. And the missing thing was Ceres. A body that we now call Ceres, which is between Mars and Jupiter. It plays a big role in The Expanse, so you all know about it, Ceres Station. And so Pazzi discovered it, and everything seemed to make perfect sense, right? You can now put in all these numbers into the Titius-Bode law, and you get where Sirius is, and the number fits really well. This thing was discovered right where it was supposed to be. So for a very happy moment, the solar system seemed to make perfect sense. We have the Titius-Bode law, we have the mathematical description, it all looks great. And this state of everything being in perfect order lasted for about a month or two. In 1801, that's when the solar system made sense for a bit, because then more discoveries were made, and they were in orbits very close to where Sirius was found. People looked in the same plane and in a similar general direction, and they found more bodies. So now, besides Sirius, we have Pallas, Juno, and Vesta. They were discovered in the 5 or 6 years following Pazzi's discovery of Sirius, so now we're up to 11. And it's not so great anymore, because at the n=3 place in the Titius-Bode law, we now have 4 bodies, okay? That's a little weird. Maybe it's not quite as weird as having none at all, but still it wasn't really making that much sense anymore for another 40 years, until the next thing happened. So now here we have another description from that time. This is, I think, from the 1830s. And here you can see that Sirius, Pallas, Vesta, and Juno were included among the planets, right? They were same as the other one, the same status as Jupiter and Mercury and all the classical ones. And we have another fun thing which you can see down towards the right. Here Uranus is called Herschel. Why Herschel or Uranus? Well, when William Herschel, he was a guy from Germany, but he lived in Britain, and he was working as an astronomer for the King of Britain. When he discovered Uranus, he was going to call it after his employer. So it was going to be called Georgium Sideris, I think, Latin for George's star, because George III was the king. And why shouldn't we name something in the sky for all eternity, for centuries to come, after that guy who's paying me right now? And people from France said, no way. And people from the United States, where this chart comes from, said, we're just going to call it after the guy who found it, because that's still better. And from Germany actually from the Bode guy, I think, came the proposal of calling it Uranus, which is, a mythical figure from Greek mythology, and everything was pretty much back in order, but in some historical sources you can find it called Herschel for that reason, because it was not going to be called George. Okay, and then came the discovery of Neptune, which was then the 12th planet, because we already had the 4 between Mars and Jupiter, and now Neptune. Now, Neptune was found not by looking through a telescope in the first place, but by looking very closely at the way that the other bodies in the solar system moved, especially Uranus. Because if you look at Uranus, then you find that its orbit is somehow perturbed. If you apply Newton's laws to describe the orbit of Uranus, then something doesn't fit quite well. And you can use mathematics and try and find out, okay, maybe there's another planet further out in the solar system, and its gravity is somehow perturbing, it's disturbing the orbit of Uranus. It's kind of tugging at the thing. And you could use that to predict where this further out planet should be. And that's what Urbain Le Verrier, which is the guy in the picture, a French mathematician, did. And actually, about the same time, John Couch Adams, a British mathematician, was doing the same thing. And now these two are having the problem that we also heard about in the talk before. The funding agencies were not going to help them out. Because these two pretty much unknown mathematicians were writing to the directors of the astronomical societies and of the biggest observatories in their countries, and they were saying, look, I did some calculations, and here's all 30 pages of them. I think for Verrier it was actually 100 pages. Adams managed to do it in 30 pages, but he was being less precise. And they said, please go look at somewhere over there. I swear, it's going to be there. And the directors of the observatories were saying, no, we got nebulas to look at. We've got other things. We've got comets to follow. We're not going to look for some planet because some mathematician comes and makes a suggestion. And John Couch Adams was kind of intimidated, and he said, oh, well, okay, maybe later, maybe I'll write again sometime. And he was forgotten. But Urbain Le Verrier said, well, if you're not going to help me, I'm going to write to other people. He wrote to Britain, which is how they realized that, wait, we also had one of our guys making the same prediction, right? If it's one of our guys, well, what would he do? What did we do about it? Oh, we ignored him, right. Well, now we've got this French guy, and he's saying the same thing. Let's make it so that the French don't discover the planet first. Let's listen to our guy now. let's listen to our guy and find the planet. So that's how they scrambled in Britain. In France, nothing was happening, and so Urbain Le Verrier said, I'm through with talking to directors of any place. I'm just going to go and write letters to astronomers who are actually using the instruments, who are out there every night in the cold looking through these things. And he wrote his proposal to Johann Gottfried Galle, who was observing in Berlin. And actually, the same night that Galle received the letter from Urbain Le Verrier, he looked at it, and what Verrier and the Brits could not know was that in Berlin at that time, in the hands of Galle, was one of the most up-to-date and precise star charts that anyone had at that time. So all Galle had to do was look at the respective part of the sky and look at all the stars that he was seeing and find the one that's not in his list, because he's got the best list of stars in that century. And so he looked, and he actually found Neptune. He found the planet that was going to be called Neptune. And that was a great discovery, and then the French were very happy, and the Brits were very angry. And the Germans were all like, hey, you know where the telescope was standing that made this discovery? And that's how Neptune was discovered. And actually, Neptune now doesn't fit with the Titius-Bode law at all. So the Titius-Bode law is now basically forgotten. And with this squabble came actually a kind of war of the press. So in the British press, they were saying, oh, look, the French, they stole our planet. We had this guy, Adams, and we listened to him so well, and we were going to find his planet. But the French, they stole it. They kind of found it first, and then they collaborated with the Germans, and it's an outrage. And while all this was going on in Europe, there was an astronomer in the United States, Benjamin Peirce, and I mean, look at him. How much fun do you think it would be to get into an argument with this guy? Exactly. He was a very, very difficult character, but he was right in one thing. He noticed that in past observations, Neptune had already been seen, but nobody had recognized that it was Neptune. In astronomy, this is called a pre-covery. When something that's going to be discovered later is already in your notes, there was no photography back then, so it wasn't photographs. It's already in someone's notes, but they didn't recognize it. It was actually recorded as some star among many others. But the Americans figured this out, and the Americans in that time, scientifically, astronomically, they were nobodies. They had just gotten started with their country. What were they going to tell us? But Benjamin Peirce was actually right about having a better calculation of Uranus's orbit, and the reason why Neptune's orbit. The reason why his calculations of Neptune's orbit were much better than all the European calculations was that he wasn't bound to the Titius-Bode law. He had recognized that we don't need to follow this. There is no rule made by God that the solar system should follow, so the numbers come out nice. He just said, look, I have better data, I have a better calculation of Neptune. And the Europeans, they were all fighting with each other, right? The Brits and the French and the Germans, and they were looking over and saying, who are you guys? We don't believe your calculations, but still the Americans were right. Now, immediately after that, so Neptune was the 12th planet, immediately in the months following, more asteroids were discovered. And it was getting ridiculous. It was getting out of hand, because between Mars and Jupiter, we now had dozens of new asteroids popping up all the time. I found here a really great example of an illustrated astronomy sort of schoolbook sort of thing. You know, for the interested public, telling you what the solar system looks like. And you see that we've got a bunch of asteroids there inserted into the inner solar system, and you can actually find different editions of this online. And if you look at the 5th edition from 1849, you see that it says, well, how many planets are there in the solar system? Well, it's 16. You see, there's the 8 big ones, and then there's 8 other small ones. And just a couple of years later, 15th edition in 1855, they're already up to, well, he doesn't even do the sum anymore, right? He doesn't write it's 31 planets. He just writes, okay, we've got 8 large ones and then 23, and they kind of updated the chart on the bottom left there, but they didn't do a new drawing, the big drawing. They were not going to change that to insert new asteroids every month. That was tedious. So that was when the solar system started to actually make less and less sense, because what were we finding all the time? And here we've got 2 publications from Germany, and they basically admitted that, okay, it's getting ridiculous. We can't even assign symbols anymore. So classically, all the planets had these symbols. You probably recognize the Venus system, which is also for femininity. And then on the right, you see, okay, we're just giving up on these symbols. We're just putting numbers now, because there's so many, we can't be making up symbols all the time. And that's when the inner solar system got really crowded, basically. And now Urbain Le Verrier enters the stage once again, and he's got an idea. Because at one time, when he was discovering Neptune, he was looking at the orbit of Uranus, and he was seeing perturbations, and he was using clever mathematics to try and find out if there was another planet tugging there. Well, there were also perturbations of the orbit of Mercury, right next to the Sun, right in the middle of the solar system. And these perturbations, you could also apply the same kind of mathematics. And Urbain Le Verrier said, well, I know how to do that one. So he hypothesized that a planet called Vulcan was actually further inside from the orbit of Mercury, even closer to the Sun than Mercury. There was this planet called Vulcan, is what he says, what he proposed, and then made calculations about and made predictions where you're going to find it. Now, there are very few charts of the solar system. This is actually the only one I found that include Vulcan, because it was always kind of a theoretical idea. But for a time there, between 1860 and 1880, many people were taking this Vulcan idea quite seriously because Urbain Le Verrier, well, he was the guy who found Neptune. Who are we to argue that, okay, but this Vulcan thing, it probably doesn't exist? People were going out and making many observations. But if you try to find a planet that's very close to the Sun, you have to look very close to the Sun. And how do you do that? Well, you have to have a filter, but then the Sun is going to be too bright anyway. You can look during a solar eclipse, right? So the moon is blocking out the Sun, and at that moment you can look right next to the Sun to see if a planet is there. Or you can look for transits, where this hypothetical Vulcan planet would wander across the disk of the Sun, and quite quickly. But you also have to have filters, and you have to make very good well, photography still wasn't around in that time, so it was quite difficult. Many people were looking for Vulcan, and during the Great American Eclipse of 1878, we see here a picture of well-known astronomer Maria Mitchell from the United States, setting up observatories there. Some people said they found it, most people said they didn't, and there were many, many astronomers looking. And then shortly after, the one guy that had announced the discovery with the most, Urbain Le Verrier, was already dead, and the one guy that had said, I definitely saw Vulcan, he also died. So now nobody was really alive anymore to really say that Vulcan definitely does exist, and at that time, everybody just sort of forgot about it. Oh, remember when we thought there was a planet Vulcan next? Let's not talk about it. It didn't turn out to be true. But there still were the perturbations of the orbit of Mercury. You couldn't discuss those away. And they were solved only a few decades later when Albert Einstein developed the general theory of relativity. And there it is explained that because the orbit of Mercury is eccentric, it sometimes goes closer to the Sun and sometimes a little further away, that the bending of space-time actually gives a little kick to the orbit of Mercury. And this is the explanation, and not the fact that there would be another planet called Vulcan. But I won't give Urbain Le Verrier too hard a time about that. I mean, 150 years before Einstein, he really just couldn't have known. Okay. It's getting more and more ridiculous. I mean, the books are now saying, yeah, the books are mostly saying we've got 8 big planets, and then there's a whole bunch of other things. They were getting to be called the minor planets, in German Kleinplaneten. And these minor planets were not really counted with the big ones. But now another big one appeared on the scene. So now we're up to, well, more than 1,000, but also Pluto. And Pluto was discovered by Clyde Tombaugh. And actually, this was also part of a campaign, a dedicated campaign of looking for another body beyond Neptune, where people were saying, oh, look, the orbits look a little weird, and let's look very closely at the sky with the best modern telescopes that we have right now. We might find another planet. And it's actually Clyde Tombaugh getting the credit for discovering Pluto is one of the rare instances where you have a big observatory and an important director who has all the money and all the connections, just hiring some young guy. I think he was 27 at the time. Yo, you go look at these thousands of photographic plates for 2 years, and then tell me if you find a planet or something. And Clyde Tombaugh actually found Pluto, and he actually got the credit for it. So if you now look up, ask anyone who discovered Pluto, well, it was Clyde Tombaugh, and not just the director of the observatory, which is a nice break, because normally, as we know, it's the big shots getting the credit for the discoveries when others were actually doing the work. And now we move into the solar system as we knew it during, like I said, our childhood of us old people. But now the asteroids are excluded, and it's hard to find out when exactly this happened. The best I found out is that during the 1950s and 1960s, astronomers and connected people just kind of stopped referring to the minor planets as planets. they sort of silently changed the definition to say, okay, we got stuff orbiting the planets, these are moons, and we've got stuff orbiting the sun, these are planets, but then we've also got this whole bunch of little stuff, and we don't want to count them all, so we just take the biggest, 9, and these are now the planets of the solar system, and they included Pluto. This was the view of the solar system up until the beginning of the 90s. But actually, for Pluto, Pluto had a great start. People thought it was a large planet and everything. But already in the end of the 1970s, so about 30 years after the discovery of Pluto, it was starting to go downhill. 40 years. It was starting to go downhill for Pluto. And we now come to the third revolution, when things were happening in the outer solar system that people were not expecting. And this is about trans-Neptunian objects and Kuiper belt objects and extreme trans-Neptunian objects. Well, the name says it. A trans-Neptunian object is just something that's behind Neptune. And Kuiper belt objects are named after Gerard Kuiper, which was an astronomer originally from the Netherlands, and he kind of proposed that there would be a number of bodies beyond Neptune, and this is now called the Kuiper belt. And the way down for Pluto began when its large moon Charon was discovered. So Charon, the largest moon of Pluto, was discovered, and you see, well, it's not digital data. Obviously, it's a photographic plate, so this is chemical data, if you will. But you see the bulge there on the left, right? It's not a round ball. It's got this thing towards the top, and that's actually the large moon of Pluto. That is Charon. And when Charon was discovered in 1978, it immediately allowed a calculation, very easily, to determine the mass of Pluto. So once you see something orbiting something else, it's very easy to determine the mass of the thing that is being orbited. And for Pluto, it turned out that it was really small, way smaller than Mercury, and really the tiniest planet, and definitely not one of the big ones, actually. And this was when it started to go down for Pluto. I see a plushy Pluto there in the first row, and it's being, yeah, it's being comforted. I also have one of these, and I like it very much. But more stuff was being found, and now we can think back to the years after 1801, right? Between 1801 and the 1850s, when more and more things were being found between Mars and Jupiter, and people were saying, "Oh God, we got to start counting, right? Are we up to 16, or is it 18 planets already?" And this was starting again in the outer solar system. This is pictures of the discovery of 1992 QB1, which was actually just a technical designation that encodes when exactly this object was found. But it came to be known as QB1, that was kind of its nickname. And it was the first trans-Neptunian object after Pluto and Charon to be discovered. And so people were saying, uh-oh, there's more stuff in the outer solar system than we knew about. And more objects were being found. I think by the early 2000s, we were up to hundreds of trans-Neptunian objects. And then there were some which became really prominent because they were really weird. This is a discovery picture. This is a Hubble telescope picture of Sedna. And Sedna has a truly extreme orbit. If you look at the little teeny tiny rest of the solar system towards the right there, that's Pluto way on the outside. And Sedna has got this extremely eccentric orbit, and it takes tens of thousands of years to go around the sun. And people were saying, well, if we got that kind of stuff out there, what else could it be that we have missed so far that is also part of the solar system? And one of the most prominent ones was Eris. Now, obviously, at a chaos event, hail Eris. It was kind of important, and it was also named kind of on purpose after the goddess of strife and discord. Because it kind of got the fight really started. Now, Eris was discovered also in the outer solar system, not quite as far out as Sedna was, but it turned out Eris was almost but not quite larger than Pluto, but it was definitely a good bit heavier than Pluto. Again, because there is a moon, and it's possible to observe the moon going around Eris. The moon is called Dysnomia, and well, it helps you determine the mass of Eris, and it's definitely heavier than Pluto. So now people were saying, oh God, not this again. Remember, 150 years ago, when we had to introduce the 10th and 11th and 12th and so on planet, we're not falling into that trap again. No, sir. And this is the context of the 2006 decision of the International Astronomical Union to say, look, we've got the 8 planets, and they're the big ones, you know them, But we also have these dwarf planets now, because we keep finding all of these objects in the outer solar system. And these objects are all out there, and we don't want to start introducing the 10th and 11th and 12th planet, because, okay, Eris would definitely have to be a planet if Pluto keeps being a planet. But then what about Sedna, Quaoar, Haumea, Macae? Some of these are too small, some of those are on the brink. What is even a planet anymore? And that's why they said, okay, we introduce new rules. You have to be orbiting the sun, you have to be not a moon, and you have to have cleared your immediate surroundings. You have to be kind of the only planet on the block in order to be counted as a full planet. And this obviously also discounted anything in the asteroid belt, because the asteroid belt is just full of stuff. But Ceres actually got made into a dwarf planet. So Ceres is now the new brother of Pluto. And they're both dwarf planets, and a number of other objects are as well. And this is kind of the new order that the solar system has found, right? We got the 8 big planets. We got a lot of other stuff. Much of it is in the asteroid belt. There's also some stuff out beyond Neptune. But these are not the real planets. They're dwarf planets or asteroids or some things we haven't mentioned, centaurs or comets, little stuff. But of course, astronomy keeps evolving. And this guy, Mike Brown, he calls himself the Pluto Killer. That was his Twitter handle, I think, most of the time. He wrote this book, How I Killed Pluto. He's not even a member of the International Astronomical Union. He didn't even take part in the vote, but he still got the International Astronomical Union to vote Pluto out, so he's being kind of smug about it. And he was involved in the discovery of Sedna and Eris and many of these outer solar system bodies, which is his claim to saying, well, Pluto had it coming. It's just not the only body out there, and I helped determine that. And then he said, what if we had another planet out there? He called it Planet 9, and it was all over the news 10 years ago. And let's look at his proposal of Planet 9, because he's proposing something way bigger than Pluto or Eris or the other bodies out there. He's proposing something along the lines of a body between the size of the Earth and Uranus, mostly. And the idea behind his and some collaborators' theories of Planet 9, this is a theory. Some astronomers follow it, many don't. It's not actually, oh yeah, I forgot. It's not the same as Planet X. Now, Planet X was something of a meme in the astronomy world in between the 1950s and the 1980s, where people were saying, I think there's something out there between Neptune, not talking about Pluto, I'm talking about something big, and this was called Planet X. Now, this book is actually a fantastic book, and if you enjoy this talk, you will definitely enjoy this book, The Hunt for Planet X, which is about the history of astronomy and how we understand the solar system. But this, again, is also different from the crackpot conspiracy theory, something is going to slam into the Earth and there's going to be an apocalypse or whatever, kind of thing that is also sometimes called Planet X. So now we have 3 different things, right? We have the historical Planet X that people sometimes suspected back in past decades. We have the crackpot conspiracy theory Planet X, which definitely doesn't exist. And we have Planet 9, which is what Mike Brown, the Pluto Killer, is talking about. And I think this picture sums it up in quite the best way. Now, these are all extreme TNOs. So all of the orbits that you see there are the orbits of objects that are out beyond Neptune, but their orbits are extreme in a way that they are very elongated, they go very far out from the sun, they are very inclined, right? They're not in the same plane as most of the other planets, but they go a totally different way. And what Brown and his collaborators are saying, look at how they're all clustered. They all kind of point in mostly the same direction, is what he's saying. And the reason for that has to be a really big planet, which is way out beyond Neptune, and it's perturbing all these, right? It's kicking all these little bodies out into their extreme orbits, and just the fact that their orbits look like that is evidence for the fact that this planet should be there. We just haven't found it yet. And like I said, he makes some good arguments. Other people have good counter-arguments, saying, for example, that, well, we should have seen it by now. There's a lot of observational programs going on looking at the outer solar system and even infrared cameras looking for very dark bodies, and we have never found anything that big. I mean, if it's something between the size of Earth and Uranus, we must have seen it by now. Another counter-argument to this Planet 9 hypothesis is to say, yeah, you found all these extreme TNOs, But there's probably a bunch more, and this is probably a selection effect. It's probably an effect of where you were looking at the time that you were discovering them. If you look that way and you find, I don't know, 10 objects whose orbits look weird, maybe if you looked that way, you would have found another 10 objects with equally weird orbits, but they could be equally distributed throughout space. And this is the counter-argument to say that, well, you have selection effects, you were looking mostly in one way. Now, Mike Brown would say that this is not the case, but this is kind of where the debate stands, and it's kind of stalled. The idea of Planet 9 made a big splash 10 years ago, and it hasn't really progressed very far. All the arguments are on the table. Most astronomers don't think that they are convincing. And so this is where the solar system is. We've got this handy little diagram. In the talk before, we heard that astronomers are really great at naming things. Here you see that astronomers are also very good at classifying things in a very clear to understand way. And if Planet 9 or Planet X were to exist, then of course the blue planets box would have to extend downwards towards the Trans-Neptunian objects, but exclude the dwarf planets. I bet that someone on Wikipedia already has an SVG file ready for when that happens. And this is kind of where we stand. The solar system is a weird place. There's a lot going on. We've got a bunch of large bodies. We've got many, many, many small bodies. It's sometimes hard to categorize them, and it's sometimes hard to exclude the way that we humans like to think about the universe from what is actually out there and happening. And this is how throughout the decades and the centuries, we've had the 7 classical planets, but then the first revolution happened and we realized that the sun was actually in the center, so that gave us 6 planets until Uranus was discovered, and we got 7 planets. Right before the Titius-Bode law was gloriously completed in 1801 to include Ceres, and basically 5 minutes later, more bodies were being discovered in the inner solar system. Neptune brought the number up to 12 in the middle of the 19th century. And by the time Pluto was found, the whole asteroids thing was getting way out of hand. So now that the third revolution of finding more stuff in the solar system is in full swing, we are back to 8 for the moment. And that is where I conclude my talk, and I thank you very much for your attention.
Okay, thank you, Michael, so far. We have around 15 minutes for questions, so if you have a question in the room, please come to one of the microphones. And I think this is microphone number 2, so please go ahead.
I think mic 2 is not open. I'm still not hearing anything. Let's see. Try again.
Hello.
Yes.
Hi. Thank you very much for your talk. It was highly entertaining and very informative. I'm wondering if I'm imagining things, but I have no idea on the subject matter whatsoever, but I seem to remember that the asteroid cluster around Ceres, that there is maybe crackpot hypothesis that all the asteroids are actually the rest of an exploded planet or whatever.
Yeah. It's not too far out there. So we basically have very, very bad ideas about how or very imprecise ideas about how the bodies in the solar system actually came to be, how planets start forming. It's getting much better since we see many other planets. With exoplanet discoveries, we see other solar systems forming, and this gives us a much better idea of how a solar system forms. But back in the times when we only knew our own system, we had very bad ideas, very bad ways of finding out how a solar system is actually formed. Think of somewhere where there's only adults. You've only ever known adults. Everyone is an adult, and you don't know what children are. How do you describe children? What do you think children look like? How do children work? You would have no idea. And it was this situation that we had in the solar system. And there is a go-to theory of when we don't know how something happened, it's probably that, which is large collisions. Large collisions are probably an explanation of why Uranus is rolling on its side. Large collisions are pretty much definitely the reason how the moon was formed around the Earth, and it's relatively large. Large collisions are probably the reason why Venus is turning backward. And so it makes kind of sense to posit that a large collision may have created the asteroid belt. But a different theory is actually physically considered more plausible at the moment, which is that the gravity of Jupiter is so dominant, and it even creates sorts of gaps where there is gravitational resonance in the inner solar system. So there are places, there are orbits where almost no asteroids are, because at that point they would have a resonance and be kicked out by Jupiter all the time. And so the leading theory of how the asteroid belt came to be is that all the planets were forming, and in that area there just wasn't a chance, because gravity was so wild, for things to coalesce into one body. But if we look at single bodies, there is actually some hints at asteroid families. So this is where you can look at the light and you take spectra and you can see what metals and what stones they are made of and so on. And there are actually a number of asteroid families where you can say, okay, these 20 or 30 asteroids, they probably all come from one, which was then struck by something. So we see small families in the asteroid belt. Most of the astronomers don't believe that they all come from one and the same body. It was probably rather the case that a large body just didn't form in that place.
All right, let's jump to mic 1.
That was great and super accessible. Thank you. You said that once a body is identified as having a satellite, it makes it really easy to work out what its mass is. Can you explain, like I'm 5, how that works?
So the more heavy something is, the faster you need to be in an orbit around it. I could orbit a small asteroid, a 10-meter asteroid. I could orbit it really easily. I could just be throwing pebbles and keep myself in an orbit. But to orbit something that's very heavy, like the Earth, for example, you have to have a speed of nearly 8 kilometers per second, because otherwise the gravity is so strong that you just fall down. And the trick of being in an orbit around something is to basically be so fast that you're kind of falling behind the horizon. You're so fast that, yes, you're falling down all the time, you're in free fall, but you don't actually hit the thing. It's what Douglas Adams in The Hitchhiker's Guide called falling down but forgetting to hit the ground. That's actually, from an orbital mechanics standpoint, a very good description of how you orbit something. And so, if you see how fast something is orbiting around something else, then you have a very good idea of how heavy that thing is that it's orbiting around.
All right. Microphone number 4, please.
Hey, yeah, very similar question to the first one, but are all of these objects that you've been talking about spherical? And if no, which ones are not spherical? And why?
Good question. Very good question. In the asteroid belt, there is only one body which is spherical by its own accord, probably, which is Ceres, the largest asteroid with a diameter of about 1,000 kilometers. There is another one which is considered to be actually a little too small to be spherical, but it still looks spherical, and this is Hygeia. It's one of the first dozen or so asteroids that was discovered. You will automatically be spherical as a body in the solar system if your gravity is heavy enough, because you start pulling in all the stones and then all the metals and everything. You start pulling it into yourself with your own gravity, such that a sphere results. And if that happens, the body is said to be in hydrostatical equilibrium. It's so heavy that it just pulls itself into a ball. This is the case for Ceres. Like I said, there is Hygeia, which is seen to be spherical, but actually is probably not heavy enough to actually be that. But all the larger bodies are spherical of their own accord just because of their own gravity.
Right.
And the smaller ones, actually, it's fun, because if you look at those which are not spherical, we used to say that they were all mostly potato-shaped, so like random stones, ellipsoids, kind of. But in past years, we've seen, for example, the comet that was visited by the Rosetta probe, the Churyumov-Gerasimenko 67P, and we saw the Arrokoth, the body that is out beyond Pluto, that was visited by the New Horizons probe after it had passed Pluto. And these are bilobates. They look like rubber duckies. Right? You got a rubber ducky which is basically like 2 little balls stuck together with a thin neck in between. And we now know a comet and a Trans-Neptunian object which both have this shape, and they were probably created by 2 smaller objects touching and kind of growing together but not fusing completely into one body, so you get these rubber ducky bodies. And some even smaller ones are kind of diamond-shaped. It's as if you took a diamond and you turned it around to make it a 3D object. This is, for example, the Ryugu asteroid that was visited by the Japanese Hayabusa probe. Or you have the Bennu that was visited by the OSIRIS-REx space probe from NASA. These have this diamond shape, and it's only in recent years, the last 10 or 20 years, that we've started to visit these bodies with spacecraft, because we can't see their shape with telescopes from Earth. They're just way too small for that. And since we have started visiting these very small bodies with space probes, we've seen that there are all kinds of funny shapes, and it's probably going to get funnier the more of these bodies we visit.
Okay, let's take a question from the internet from our signal angel.
Are there any unexplained differences between our planet system and other planet systems?
Oh, that's a very good question. Yeah, we see a bunch of types of planets in other solar systems that we don't see in ours. One of the big ones is what's called hot Jupiters. Hot Jupiters are large gas planets of the mass of Jupiter or even more, but they are very close to their stars. We see these around small red dwarfs, which is also due to the way that we detect exoplanets, so finding these kinds of planets around these kinds of stars is easier than others. But hot Jupiters are one thing that we don't see in our own solar system. Another thing that we don't see is super-Earths. We know maybe a dozen or 24 super-Earths in other solar systems, and these are called that because they're larger than Earth, but they're definitely... Oh. Continue talking. Yes. They are larger than Earth, but they are definitely not a big gas planet like Saturn. They are somewhere between Earth and Uranus. And so these... little confused with the microphone, but the speakers are going to work again in a minute. So they are between the mass of Earth and the mass of Uranus, and these are called super-Earths. And actually, we don't even know if the super-Earths have a thin atmosphere like our Earth does, or if they have a thick atmosphere like Uranus. There's probably things in between. The universe doesn't want you to hear this, but I'm going to say it anyway. So we see other solar systems forming. We see them forming other planets. The key to all these mysteries and many of the differences between our solar system and ours is probably planetary migration, which is the suspected fact that after a solar system has formed, the planets start tugging and sort of kicking at each other with their gravity and sorting the whole thing anew. So there's probably almost no solar system which looks the same way as it did on the first day after the planets formed, because they all kicked each other around over the billions of years that pass afterwards. And that's probably what happened in our solar system and in others as well. But it's a very active field of research. This question of how do other planetary systems look different from our own is one where there are many exciting answers still to be found.
Okay, let's jump to mic 3.
Hi. On one of your slides, you had a really nice chart of like the set of like hand-drawn orbits in the 1700s, and I noticed that the orbits weren't like centered on the same point, and I wondered if you have any knowledge like why they chose to represent it like that.
Let's see. This is circular. We had the historical ones. Do you mean this one?
No, it was still earlier.
Still before, so...
Yeah, this one.
Okay. What is represented here is eccentricities. So actually, the orbit of Mercury takes it quite a bit closer to the Sun at some times than at other times. And this is called eccentricity, is where you're not going around another body in a perfect circle, but you are sometimes closer, and when you are closer, you're moving faster, and you are sometimes further away, and while you are further away, you are moving slower. This is what Kepler's laws first poured into mathematics. And I would say that this is actually mostly a representation of these eccentricities. For the large bodies like Jupiter, it's pretty much circular, because with its large gravity Jupiter experiences a lot of tidal force between it and the Sun, and tidal forces tend to circularize your orbits. But if it looks kind of weird, it's probably mostly because of Mercury in the inner solar system, which has a tilted and quite eccentric orbit. Yes.
Thank you. Let's go to mic 4.
Okay. I have a question regarding the definition of the planets. Does it have to take into account the planetal orbit of the planets? or the origins of the planets, because I think I've read it before. When planets form from the proto-solar system, the planets will form from the same cloud gas, will be on the same planet, same plane of orbit, and other objects that are part of the solar system but not on the same plane are actually objects that were caught by the gravity of the sun.
Could be, yeah.
For example, Pluto,
it's quite inclined. Pluto has, I think, like a 17 or almost 20%, a 20-degree tilt towards the ecliptic plane. Yes.
So yes, so maybe it's likely that it's not the object that was formed from day one from the solar system. So it couldn't be planet for this reason, or.
Well, there's another more. There's another simpler explanation. So you're saying that Pluto's orbit looks weird and it's tilted and it's quite eccentric. Sometimes actually Pluto's orbit takes it closer to the sun than Neptune, and other times it's still further away. But it's more likely that Pluto was kicked by Neptune at some point. So the planets with orbital resonances can sort of shuffle each other around. We have seen, as far as I know, 2 times already, bodies that definitely came from another star, and they were inside our own solar system, but only for a while, and then they shot out again. One of these looked very much like a comet. This was 2I Borisov, and the other one was on the news a lot. This was 1I Oumuamua. This was where one of the astronomers, one of the American astronomers said, "Oh, it's probably an alien solar sail or something." It probably really was a rock. That guy always talks about aliens because he wants to be on the news. But we have seen objects from definitely somewhere else, but their orbits are super eccentric. So for something to be captured into the solar system and actually orbit the sun near where the other planets are, it's much more likely that it's a body that, yes, it did form in the solar system and then it was kicked around a little. But to answer where your question got started, the definition for a planet today, as defined by the International Astronomical Unit, doesn't take into account the orbit very much. It's a 3-step algorithm. You have to be orbiting the sun, you have to be not a moon of someone else, and you have to have cleared the orbit around you of other bodies. So you're not allowed to have small neighbors, basically. And for this, Pluto was excluded because there's all manner of Kuiper belt objects around it. Ceres is excluded because of the asteroid belt, but they are basically all considered part of the solar system and probably formed here.
Thank you.
Okay, do we have another question from the internet with our signal angel?
No, the internet has not asked any.
Then we'll just continue in the room. Mic 1, please.
Thank you. Thank you for the great talk, very insightful. I have 2 very short questions. I hope it works.
I can hear you.
Because the second question is funny. So the first question is, we're learning all the time, and I think you made a great point of, like, yes, we had these epicircles, and then Kepler and Newton and Einstein. So my question is, what about dark matter? Do you think we will learn something new about the solar system once we understand dark matter?
Everything that physicists have put into theories about what dark matter probably is says that its effect is much too weak on the solar system. You see the effects of dark matter probably in how galaxies rotate, which are collections of hundreds of billions of stars, but the solar system itself should be way too small to be affected by dark matter, except maybe that there could be a ball of dark matter in the center of the sun, because that's where it would collect, and this could change the way that the sun vibrates. This is something that people actually look at. They look at the surface of the sun and how the surface of the sun vibrates, and they want to try and see if they can see a signature of a ball of dark matter way down in the center of the sun, but this is by no means proven, and it definitely would not have an effect on the movement of the planets.
Cool, thank you. And very quickly, why does Salacia, the asteroid, look like salami or salsiccia?
Yes, Salacia. You are allowed to name, so I don't know the history of that name particularly. You are allowed to name a body in the solar system if you found it, and if the International Astronomical Union thinks the name that you've chosen is not too silly. So there's probably a mythological figure, but it also works as a joke. Actually, the guy that found the moon of Pluto, the guy that found Sharon, had a wife called Sharon. But he looked it up in an encyclopedia, and he found that Sharon was also, I think it's the figure that ferries the dead souls across the river Styx in the underworld, which is where the god Pluto also exists. So it fit perfectly, and his wife Sharon was very happy.
Thank you.
All right, we're almost at time. I think we'll have time for one more question at mic 4, please.
Thanks. You've explained quite precisely what makes a planet, right? Those three things. But what differentiates a dwarf planet from an asteroid, and why is Eris a dwarf planet and not an asteroid?
That's a good question, and there the distinction is not very sharp. It's actually, you would probably say that so that there's not a fixed written rule, not an algorithm that I know of, but the general feeling in the International Astronomical Union is that to be a dwarf planet, you have to be in hydrostatical equilibrium. We had a question before about when is a body spherical in the form of a ball. It's when its own gravity can pull it into the form of a ball. And so for Ceres, we know that this is the case. For Hygeia, which is not considered a dwarf planet, it could be the case, and then it would have to be included. For many of the bodies out in the Kuiper belt and the Trans-Neptunian objects, we don't actually know their shape, we don't see it, we can only guess from the mass. But here's a funny thing, the International Astronomical Union once defined a small number of dwarf planets, I think actually 6 or 7, and since then, because of all the drama, they just stopped registering new dwarf planets. Bodies in the solar system continue to be found, and many of them fit the criteria of being a dwarf planet, but the International Astronomical Union is just not taking any calls on the subject.
All right, this concludes our talk. Thank you so much, Michael. This was highly entertaining.
Thank you.